let's review some limits and get all ready for our test here. So here, first question here. We've got a function here, and we want to find these limits for that function. First, we want to find the limit as x goes to 0. Well, if we plug in 0, first of all, we can see that it doesn't cause problems, right? So we get 0 squared. We always want to just plug things in first, right? 0 squared minus 16. And we can evaluate that, right? It's a negative 16 or negative 20 over 16 negative. And negatives cancel, and that's 5/4. Okay. What about as x goes to infinity? Well, as x goes to infinity, the small terms don't matter. So this is equal to the limit as x goes to infinity of this simplified function. We can cross all these out because they're at when x is infinity, or when x is very large, these smaller degrees don't matter. So we have x squared over x squared, and that's just simplifies to 1. X squared over x squared is 1, and the limit of 1 is just 1. Okay. All right. And the limit as x goes to 4 of f of x, well, if we plug in 4, we notice we have a problem. So we need to clean this up. So let's rewrite the limit as x goes to 4. Yes, as we've been talking about, it's a good idea to bring this limit along. We haven't evaluated that. Unless you want to work down here, and simplify the function and then bring it up. You could do that. I don't think that's best, but you can do that if you want to do that. Do some side work. Well, anyways, we want to factor the top, and the top, let's unerase this stuff here. So the top, factoring, two numbers that add to 1, multiply to negative 50, that would be x plus 5 times x minus 4, all over, factor the bottom, that's x plus 4 times x minus 4, difference of 2 squares. And so, good news, that problem cancels. That's a removable discontinuity. That's the term for it. So we have removed the discontinuity or the problem there. And we just have x plus 5 over x plus 4. And 4 is no longer a problem, so we can just plug it in. Plug it into all the x's. And we get 4 plus 5 over 4 plus 4. And that's 9 plus 4. 9 plus 8. 9 over 8, sorry. 9 over 8. Okay? So here at this step right here, we are evaluating the limit, because now we can evaluate it because we can plug it in. We can't evaluate it at the beginning, because if you plug in 4 to start, you're going to get zeros on top and bottom. And 0 over 0 doesn't tell us anything. It's what we call indeterminate. All right, well, we got a function here we want to graph. We've got 1 minus 2x. All right, so that has that's the same as negative y equals negative 2x plus 1. That's a line. Okay, so y-intercept of 1 and a slope of 2. And this is everything to the left of negative 1. So the graph, slope of negative 2 that is, goes down like this, up like this. Okay, so it goes down there, goes up there. But we want everything to the left of negative 1. So we're going to erase everything that doesn't have an x value. That is less than negative 1. X value has to be less than or equal to. So we have or equals to, so that means we're filled in here. Now we're going to graph this line, y equals x minus 4, y-intercept of 4, negative 4 that is, slope of 1. Okay, something like that. And this is for all values greater than negative 1. So let's go ahead and put a open dot there. So it is a function. There's only one value for each x, one y for each x. Okay, So what's the limit as x goes to negative 2? Well, negative 2 right here, that there's not a hole there. So we can say the graph from the left and the right would go to a height of 5. So that limit exists. The limit as we go to negative 1 from the left, remember this means from the left, so we're coming from the left. What is the y value we're approaching? The y value we're approaching is 3. As we come from the right, the limit as x goes to negative 1 from the right, that's what this means. So we're coming from the right down this line, and the y value we're approaching is negative 5. Well, are those the same? No, they're not. So negative 1 is approaching different values from the left and right, so this does not exist. The limit, the overall limit, not the left and right limit, these are the left-hand limit, the right-hand limit. This is the overall limit, so the overall one doesn't exist because they're not going to the same place, right? All right, here's a good one. Let's create a single function so that we have these things. We've got a removable discontinuity at x equals negative 3. Well, if it's removable, that means that we have a factor that cancels. So we got to have x plus 3, and it needs to cancel, so it needs to be on top and bottom. We have a non-removable discontinuity at x equals 2. Well, that means that there is an asymptote at x equals 2, and so x minus 2 is our factor, because when you plug 2 in here, it causes a problem, and we can't remove it by canceling. So there it is. Directions say we don't need to simplify, so there's a good example. Now, there's lots of options. I could throw a number in here like 2 or 12, and that would also be true, okay? Or I could throw other factors in here. I could throw in an x plus 12, okay? Something that doesn't cancel, and that would still have these features. So there's lots of options, but the simplest option is this one here that has just those features, okay? It's not the only function, but it is the simplest, all right? On to the next page, let's evaluate some limits analytically here. So we have an expression here. Now first we should probably plug in 2 to see if it causes a problem, and we care mostly about the denominator. When we plug in 2, we get 4 plus 4 times 2 is 8 minus 12, and that is 0, right? Okay, so that's 0. So when you plug in 2, it doesn't work. So all right. Now most of the time here, that's the case. We're not going to waste our time too much on problems that they just plug it in, but it's worth a check. All right, so what do we need to do? We need to rewrite this limit. We need to factor the top, x plus 2 times x minus 2. It's a difference of 2 squares. Two numbers that add to 4 and multiply to 12. That's x, let's see, plus 6 minus 2, right? There we go. Okay. And 2 of those cancel. So 2 is no longer a problem. And so we can simply find the limit as x goes to 2 of x plus 2 over x plus 6. And now plugging things in is not a problem. Plug it in. And we can evaluate the limit by plugging it in. So evaluating, we have 2 plus 2 over 2 plus 6. And that's just 4/8 or 1/2. Okay. Well, what if we have this radical? Well, you can't really factor it very easily. So we need to multiply by the conjugate. So multiply this, slap some parentheses around that, by 3 plus the square root of 5 minus x. Multiply this by 3 plus the square root of 5 minus x. So the conjugate, remember, changes this sign to plus. Don't mess with this sign. Okay, the sign in between the two terms is what we're changing. Okay, so when we do that, we get the limit as x goes to negative 4. The top, nothing's going to happen there. X plus 4 times 3 plus the square root of 5 minus x. Leave it alone. Don't distribute that. Don't make a mess out of it. The bottom, square the first. 3 times 3 is 9. Minus, square the second. The square root of 5 minus x squared. And that is in parentheses. Don't forget the parentheses there. 5 minus x. So when you simplify the bottom, don't forget to kind of distribute this negative here. Okay, we have our limit as x goes to negative 4 of x plus 4. The top, we're just going to leave it alone for the moment. Square root of 5 minus x. And on the bottom, 9 minus 5 would be 4. And minus negative x would be plus x. All right. And 4 plus x is the same as x plus 4, we know, so that cancels. And so we're left with the limit as x goes to negative 4 of this thing in the parentheses. And we can go ahead and plug that in. Let's evaluate the limit here. So we're going to have 3 plus the square root of 5 minus, plug in negative 4, because that's what we're finding the limit here. Plug that in. That's 5 plus 4, that's 9. The square root of 9 is 3. 3 plus 3 is 6. Okay? There you have it. So again, we're changing the limit until we can actually plug it in and evaluate. All right? All right, little trigonometry here. We have two special limits that we're looking for. We know the limit as x goes to 0 of sine x over x. That goes to 1. That's one we need to have memorized. The limit as x goes to 0 of 1 minus cosine x or cosine x minus 1. It doesn't matter which way it goes. That's going to go to 0. All right? So with that in mind, we're looking for those couple things, one of those to show up. So we're going to manipulate this expression algebraically. So we have tangent, that's sine of 3x over cosine of 3x times the sine of 4x. Okay. Well, it doesn't quite look like those. Now the key here is that these match, this x and this x. Okay, they match. Notice this 1 minus cosine isn't going to show up. That's fine. Okay. Now actually, this problem turns out to be a whole lot simpler than it looks. And a better problem would be if this was cotangent. But oh well, it's not. So I think the problem was written wrong. But notice this, we can just plug in 0, and it's not a problem. So don't forget that. We can just plug it in. So plugging in 0, we have the sine of 3 times 0 over the cosine of 3 times 0 times the sine of 4 times 0. Well, what is the sine of 3 times 0? Well, it's just the sine of 0, and the sine of 0 is 0. And the cosine of 3 times 0, cosine of 0 is 1. And that's 0. Okay, well, that was kind of turned out to be not very interesting. Easy, but not very interesting. So one other problem to try and be ready for on the test is the limit as x goes to 0 of cotangent of 3x sine of 4x. Okay, so this is kind of would have been a better problem. I'll have to change it for the future. And that's going to be cosine of 3x over sine of 3x times sine of 4x. Okay, this one's a little more interesting. Okay, so we need to rearrange this. And the cosine's not a problem, but it's the sine that's a problem. So we're going to rearrange this. I'm going to leave this as sine of 3x and just kind of maybe 1 over times the sine of 4x over 1 times, and we'll just tuck this cosine over here. Now, we'd like to have something up here that matches this. So here's where we make a wish, and we say, I wish we had 3x. Well, if I put a 3x on top in this string of multiplications, I need to put a 3x on the bottom somewhere. Okay, those technically cancel, and it's worth the same thing. Well, I'd like to have a 4x down here. Okay, well, let's put a 4x down there, but if I put a 4x down there, I need to put a 4x up top. Okay. Now, what's going on? Well, now we can evaluate these limits. This first part goes to 1 because it's sine of an expression over the same expression. That's going to 1, whether it's the reciprocal or not, whether it's flipped or not. So this is going to 1. When we plug in 0 here, cosine of 0 is 1. So this is 1. And then, we got 3 times 0, but wait a minute. That x is going to cancel with this x. So those x's actually go away. All right? So we have 1 over 3 times 4, which is also known as 4/3. Okay. So the original problem, too simple. Be ready for this problem on the test or something like it. That's the idea. Okay? All right. How about a compound fraction? Well, if we have a compound fraction, there's a couple approaches. One good approach is to simplify the top and then multiply by the reciprocal of the denominator. So to get that denominator out of there. So we have the limit as x goes to 3. We need a common denominator, so we're going to need, well, this is over 1. So let's just make the denominator x minus 1 and x minus 1. So we'll have 2 times x minus 1 minus, so we have minus, put parentheses on this x plus 1, all over our common denominator that we just kind of made was x minus 1. Don't forget this denominator here. Some of us have been doing that. Okay, bring it along. We're not going to use it at the moment, but bring it along. Okay, we can clean this up now. Here we have 2 times x. Okay, let's just write it out. It would be safest. Okay, so we have 2 times x, 2 times 1, minus 2. Distribute that negative sign, minus x minus 1, all over x minus 1, all over x minus 3. Okay? Again, by bringing this stuff along, you're not going to make silly mistakes. If you don't bring it along, then you got to go back and you got to figure out what's going on. So just bring the stuff along that you're not using, including the limit, haven't used it yet, including the denominator, haven't used it yet. Okay? Bring it along and everything will just fall into place. Okay? So simplify 2x minus x. Well, that's x. Still have the limit. Haven't figured that out yet. So that's x. Negative 2 minus 1. That's minus 3. Oh, look. Okay, so that comes from the top. Let's copy this down because we haven't used that yet. Okay, and now this is like over 1, so we multiply by the reciprocal. Okay, or just change it to multiply by the reciprocal, and we're almost there. We have the limit as x goes to 3. Okay, this all cancels here. These guys cancel, and we have 1 over x minus 1. That's what's left. Denominator's gone. This becomes 1 over x minus 1. And we can plug in 3 there, and we are done. 1 over 3 minus 1, which is 1 over 2. Done. Okay? That's the idea. Well, how about some limits at infinity here? So, limit at infinity. Remember, with each expression here, all right, each polynomial, we can get rid of the small values. Well, this is not a polynomial. This is just a monomial, so leave it alone, all right? So this equals the limit as x goes to infinity. Leave the top alone. There's nothing to cancel yet, okay? But here, when we look at this, does that 25 really matter? No. So we just have x squared. When we go to infinity, really large numbers, the small numbers don't change things. When x is huge, the 1 doesn't matter. So we have x squared times x, okay? And so we end up with a limit as x goes to infinity of 4x squared over x cubed. And that's going to cancel with 2 of those. That leaves us with the limit as x goes to infinity of 4 over x. And as x blows up, this is 4 over million, 4 over billion, 4 over trillion. This is just 0. It's going to 0. Okay? It'll never be 0, but it's going to 0. That's the whole idea of a limit. We're going to that point. We're finding that wall or that ceiling, if you want. All right? Again, as we go to negative infinity here, the small things don't matter. So we got this expression on the inside. We've got pi x. Well, that's x to the first. That's a lot smaller than x to the fourth. We have minus e to the first, okay? And so that doesn't matter, okay? So we're going to have the limit as x goes to negative infinity of the square root of 49x to the fourth. We'll clean that up in a second. On the bottom, the 25 is not really going to matter. So we just have x squared, okay? And now if we clean that up, square root of 49 is 7. Square root of x to the fourth is x squared. And what do you know? The x squareds cancel. Gone, gone. And we have the limit as x goes to infinity, or negative infinity that is, of 7. Well, the limit of 7 is 7. 7 doesn't change. All right, so again, going to infinity, small degree terms can be canceled. Again, we're just comparing one polynomial to itself, all right? So don't go crossing out the x squared because x to the fourth is bigger. No, just within this polynomial, the largest degree is all we need to keep, okay? Within each term there. Or yeah, I guess each factor. Okay, in this factor, only the largest degree term matters. All right, here's a good question. So here we have an expression. We've got some unknowns a and b in it. And we want to evaluate this so that the limit as x goes to infinity is 5. All right, well, let's start by writing it out here. So we're saying the limit as x goes to infinity of 8x minus 12 over 3x minus b. And we want that to be equal to 5. Well, let's think about our infinite limits that we just worked with here. As x goes to infinity, I don't know what a is. It's just a number, all right? That's some number times x. But what doesn't matter? What can we get rid of? We can get rid of the minus 12. And as we go to infinity, as x goes to infinity, whatever number this is, b, it's a constant. That one doesn't matter. Okay? So we're saying the limits as x goes to infinity of 8x over 3x has to equal 5. Well, we now know that we can cancel these x's. So whatever a is, we have to have a over 3 equals 5. Multiply both sides by 3. This implies that a is 15. So let's use the same expression here. And now we want to evaluate the limits. We want to find the value of b, that is, so that the limit as x goes to 4 does not exist. Okay, so the limit as x goes to 4 of ax minus 12 over 3x minus b equals d and e. Does not exist. Well, if that doesn't exist, if that's the case, what does that mean for us? Well, it means that when we plug in 4, that the denominator is 0. And we can't simplify it, right? We're assuming we can't simplify it. Otherwise, if we could simplify it, then we could find the limit. But we're told here the limit doesn't exist. So if the limit doesn't exist, then that means the denominator goes to, it must be 0. 3x minus b has to be 0. So add b to both sides. Okay, and so b, as x goes to 4, right? Let me back that up here. Okay. The limit as x goes to 4, that means when we plug 4 in. So let's go ahead and plug 4 in. There we go. Don't forget that, like I just did. So 3 times 4 equals 0. There we go. So add b to both sides, and 3 times 4 is 12. So b is 12, and we'd have to have an a such that it doesn't simplify, all right? Then we would have something that does not exist, okay? A limit that doesn't exist. Okay, so there you have it. And last but not least, let's look at our graphical limits here, all right? So we want to find our limit. Here's f of x in our graph as described, okay? And so let's find these limits. So the limit as x goes to 3, negative 3 that is. Well, as we go to an x value of negative 3, we're coming to a y value of 3 from both sides. So the limit exists. It must exist from both sides. We don't have to have a value here. It's okay that there's a hole. We're just approaching the same value. How about as we're going to 2? So as x is going to 2 over here, so the y value is going to 0. The y value is going to 0 from the other side. So the limit of the function, which is the y value, is 0. Now, the limit as we're going to negative 1 from the left. That little negative 1 there means we're coming from the left. All right, well, here's negative 1. Okay, coming from the left, the limit is 1. Coming from the right, so going to negative 1 from the right, what is the y value we expect? We expect a y value of 2. And then what is the limit as x goes to negative 1? The overall limit, well, since these two don't agree here, there's a split. It's not continuous. This does not exist. Okay. And one more as x goes to negative infinity. Going down here, all right. What's happening here? Well, the function is going to negative infinity. Okay. So as we go to the left, the function is dropping. The y value is going to negative infinity. All right. Cool. Well, a little bit of intermediate value theorem. Okay. Functions f and g are continuous for all real numbers. The table below gives some values of the functions. The function h is given by this. Okay. Explain why there must be a value for w at, and then this interval, w is between 1 and 5, such that h of w is 0. Okay, well, we need to look at the endpoints, and let's find h of 1. This is, by the way, is a classic AP style question. So let's find h of 1. Now, you might be puzzled, how do I do that? This is confusing me. Well, first, write it out. Okay, h of 1, by the definition, is g of f of 1. Then start from the inside. What is f of 1? Can you find that? F of 1 is the value of f when x is 1. So that is g of 3 plus 2. Well, what is g of 3? This is not g times 3. This is g of 3. G of 3 is the g value when x is 3, so it looks like it's negative 10. So this is negative 10 plus 2, which is negative 8. So h of 1 is negative 8. All right. What about h of 5? Let's find the other endpoint. Well, h of 5 is g of f of 5. Again, write it out. What is f of 5? Well, let's go to our table. F of 5 is 7. So that f of 5 is 7. Replace f of 5 with 7, and then we ask ourselves, what is g of 7? Well, g of 7 is 25. And 25 plus 2 is 27. Okay? So we notice we get a y value below 0 and a y value above 0. So we can say, since h of 1 is below 0 and h of 5 is above 0, and we have to say that h of x is continuous. How do we know it's continuous? Well, it's made of continuous functions. You don't necessarily need to go into a big description there, but it is continuous because f and g are continuous, and h is made of f and g. All right, so it's continuous. So we need to say it's continuous. We need to say the y value 0 is in between the two y values we're looking for there. Okay, and we need to also state IVT, intermediate value theorem. So we can say by the intermediate value theorem, and we can just repeat what was said. There must be a value w for 1 less than w less than 5 such that h of w is 0. So this last little part, notice that, is just a kind of repeat of this. So that's a formal way to say it, and like I said, in most questions, you're proving this. So that is your conclusion in your if-then statement. Okay? All right. And here you go. We talked kind of quickly about this. What are the two big questions in calculus? Well, the first question is, how do we find the slope of a tangent line? How? So when we have a graph, the tangent line goes through one point, and how do we find the slope of that? Well, that's a limit problem. Okay. The second problem that calculus will address, big question that is how do we find the area under the curve? Okay. The area under a curve. Okay. So if we're looking at this graph, how do we find the area under this parabola? That's the second question that we'll address with something called integrals. Okay? All right. Well, there you have it. That's the big stuff there, all right? And so keep working hard, and hopefully that helps. Thanks a lot.